I welcome you all to lecture number 19 of this course. Now, before I start, I have got one announcement to make, that is regarding your second test. The second test of this course will be held on 14th October, that is your coming Wednesday. And we are going to start at 12 noon, exactly in the same time, our class routine time. So the exam will be for a maximum of 1 hour, the way we did the first test. And once again, there will be MCQs, and exactly in the same way, the way you did for the first test. So you'll have to send the answer to the pre-specified Gmail account. Okay, I'll be sending the instruction once again before the second test. So once again, let me repeat. The second test of this course will be held on 14th October, that is Wednesday, and we are going to start at the scheduled class time, that is 12 noon. So 12 noon to 1 p.m., maximum up to 1 p.m. Okay, and the syllabus for this test will be whatever I can cover up to 10th of October, that is a Saturday's class. That will be the syllabus for this particular the test. And I've already given you assignment 3, and the due date for assignment 3 is 10th October, all of you know, and try to submit the assignment 3 by 10th October. Okay. Otherwise, there will be late marking. Okay. So be careful about your assignment 3 and your the second test to be held on 14th October. Now, with this, let me start with today's topic. Now, we are discussing the clustering of the data, and more specifically, the fuzzy clustering of the data based on similarity. Now, as I mentioned, that clustering is a powerful tool for data mining. And the purpose of data mining is to extract the useful information from a data set. And if you want to carry out that particular data mining, you can take the help of your fuzzy clustering or clustering. Okay. Now, as I told several times, this clustering is done based on similarity. That means your two similar data points should belong to the same cluster, and two dissimilar data points should go to two different clusters. Okay. Now, there are several methods of this fuzzy clustering. For example, we have got the fuzzy C-means algorithm, potential based clustering, entropy based clustering, and so on. And as I told, that this particular clustering could be either crisp or fuzzy in nature. So by fuzzy clusters, we mean there could be overlapping of the clusters, and a particular data may belong to a large number of clusters with some membership function values. So all such things I'm going to discuss now in detail. So I'm going to start with the most popular approach of fuzzy clustering, that is known as fuzzy C-means clustering, and in short that is known as FCM algorithm. Okay, FCM algorithm, fuzzy C-means algorithm. Now, this fuzzy C-means algorithm was proposed by Weizsäcker in the year 1973. Now, here, say a particular data, uh, just a minute, I've got a phone call from the office, just a minute. Hello, হ্যাঁ 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 চলছে বলুন হ্যাঁ বলো। ভেরি গুড, ভেরি গুড। হ্যাঁ হ্যাঁ হ্যাঁ, প্রসাদ গুপ্তা, আমি একটা অনলাইন আমার ক্লাসটা চলছে, তারপরে একসঙ্গে কথা বলবো। হ্যাঁ হ্যাঁ, খুব ভালো খবর। হ্যাঁ 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 হ্যাঁ, ভেরি গুড, ভেরি গুড, ভেরি গুড। হ্যাঁ হ্যাঁ হ্যাঁ। I'm sorry, let me start. Now here in Fuzzy-Simmons algorithm, a particular data of the set may be the member of several clusters with different values of membership. Okay, and the sum of all the membership function values should be equal to 1.0. Okay, for example, say if there are 5 clusters, so a particular data point, say ith data point belongs to cluster 1 with some membership function value. It belongs to cluster 2 with some other membership function value, belongs to cluster 3 another membership function value, it belongs to cluster 4 another membership function values, it belongs to cluster 5 another membership function value. Now sum of all the membership function values should be equal to 1.0. Okay. Now here in this clustering, as I told, that this is based on similarity. So what we do is we try to minimize the dissimilarity measure between the data points. Okay. Now how to measure the dissimilarity? Now this similarity or dissimilarity, that is measured in terms of the Euclidean distance. If the Euclidean distance between 2 points I and j is denoted by dij, now if the distance is more, the similarity will be less, and if the distance is less, the similarity will be more. And supposing that the distance between the two data points I and j is 0, that means the two data points are coinciding. If that is the case, then the Euclidean distance between the two data point is 0, so the similarity will be 1.0. Okay, so what I do is we try to measure the dissimilarity of the two data points in terms of the Euclidean distance, and we try to minimize that. So we try to minimize the dissimilarity. That means we try to maximize the similarity. Now, mathematically, how to represent that particular the problem, that I'm going to discuss. Now, before that, let me take one hypothetical example that there are capital N data points and each data point is having L dimensions. Okay, so I have got L dimensions capital N data points, and now based on the similarity, so I'll have to make that particular the cluster. Now let us see how to do it mathematically. Now, mathematically, actually, what we do is we try to represent as an optimization problem. Now, how to state as an optimization problem? We try to minimize the dissimilarity. Now, this dissimilarity is nothing but, as I told, it is measured with the help of the Euclidean distance dij. So, the dissimilarity f, that is a function of mu and c. What is c? Capital C is nothing but the number of clusters, the total number of clusters, and that is defined as summation j equals to 1 to c, summation I equals to 1 to n, mu ij raised to the power g dij square. Okay. Now this Euclidean distance, that is dij, we put the square here just for simplicity, because the Euclidean distance is square root of something plus something plus something. Okay. So if I just use the square, that particular square root will be removed. Okay. And here we use a term that is mu. Mu is nothing but the membership function value. Okay, mu ij means the membership value of the ith data point with the jth cluster, and this mu ij raised to the power g, if you remember the power of a fuzzy set, that type of concept, and here the g is nothing but the cluster fuzziness. So what we do is we take the value of g higher than 1 or greater than 1, like say 1.25 or 1.5 or 2.0. Generally, we consider the value of g, that is the level of cluster fuzziness, like this. Now, subject to the condition that summation j equals to 1 to c, mu ij is equals to 1.0. That means the sum of all the membership function values for a particular data point, ith data point, with all the j clusters, or j varies from 1 to c. C is the total number of clusters, that is equals to 1.0. Okay, so this is nothing but a constraint optimization problem. And all of us, we know how to handle the constraint optimization problem if you want to use a genetic algorithm. Okay, now if you do not want to use genetic algorithm, there is another way. We can use the Lagrange multiplier. And this is actually coming under the umbrella of traditional tool for optimization. So here, this is the objective function. F mu comma c is nothing but this. Subject to the condition, this is equals to 1.0. So this is the functional constant. This is the objective function. And using the method of Lagrange multiplier, we try to combine these two things, the objective function and this functional constraint. And the functional constraint, the way it is written, summation j equals to 1 to c mu ij minus 1.0. So I bring this particular numerical value from right hand side to the left hand side. Okay. And we multiply by a Lagrange multiplier, that is lambda I. I hope some of you have studied the Lagrange multiplier method. Now, combined, the objective function can be written as f bar is a function of mu comma c comma lambda 1 lambda 2 up to lambda n, that is nothing but summation j equals to 1 to c, summation I equals to 1 to n, mu ij raised to the power g dij square plus summation I equals to 1 to n lambda I, then summation j equals to 1 to c mu ij minus 1.0. Okay, so this is nothing but the combined objective function now. Okay, and what we do is we use the calculus method. Okay, so we try to find out the derivative of a prime with respect to mu is equal to 0. Derivative of a prime with respect to c is equal to 0. Derivative of a prime with respect to lambda 1 is equals to 0. And here there are some intermediate terms, and the last term will be derivative of a prime with respect to lambda n is equals to 0. So you'll be getting a set of equations. Now those set of equations, if you solve, then you'll be getting the expression for the cluster center CC, that is the jth cluster center, that is nothing but summation I equals to 1 to n mu ij raised to the power g multiplied by xi divided by summation I equals to 1 to n mu ij raised to the power g. So this is nothing but the expression for the cluster center, that is the jth cluster center. Similarly, this mu ij, that is the membership function value of the ith data point with the jth cluster center, can be determined as 1 divided by summation m equals to 1 to c. C is the total number of clusters. So dij divided by dim raised to the power 2 divided by g minus 1, and g is nothing but the level of cluster fuzziness. So by solving that set of equation, we will be getting the expression for cluster center and your mu, that is the membership function value of ith data point with the jth cluster center. Now what we do is we use one iterative algorithm where both the cluster center as well as the membership values of the data points with the clusters are updated to minimize the dissimilarity measure. So our aim is to minimize the dissimilarity measure. So we go on updating the cluster center and the membership function values of the data points with the cluster center through a large number of iterations. And by doing that, we will be able to minimize the dissimilarity measure. That means we'll be able to maximize the similarity, and consequently you'll be getting the clusters. Now let us see how to get that particular clusters. Now at first I'll tell you the steps to be followed in this particular algorithm, and after that I'm going to solve one numerical example just to show you that for a data points, for a set of data points, how to yield that particular the clusters. So I have designed one numerical example, very simple numerical example, and I'm going to discuss that. Now the steps of this FCM algorithm. Step 1, assume the number of clusters to be made, that is C, and C is lying between 2 and n. So C is greater than equals to 2 and less than equals to capital N. C is nothing but the number of cluster center. Now supposing that I have got a data set, a set of data points. Okay, now what should be the minimum number of clusters? The minimum number of clusters has to be 2, because if it is 1, then it is the original data set, so no clustering is done. So the minimum number of clusters has to be equal to 2. And what is the maximum number of clusters? That is nothing but capital N. So C is lying between 2 and N. Step 2, choose an appropriate level of cluster fuzziness, that is G, which is greater than 1. As I told, 1.25, 1.3, 1.7, 1.5, something like this. Step 3, the membership value of ith data point with jth cluster center. So what we do is we try to initialize at random using the random number generator, so that the sum of the membership function values of a particular data point with the clusters become equal to 1.0. Okay, and the individual mu value will lie between 0 and 1, and sum of all the mu values like mu ij, j equals to 1 to c, is nothing but 1.0 for each I. So this is the way actually we start our algorithm. And as I told that we are going to start with randomly generated membership function values. So one matrix for the membership function values. Then we'll try to find out the cluster center using the information of these particular your membership values. And we'll try to recalculate the membership function values or the modified values of membership. That completes one iteration. Once again, with that particular membership function values, we will try to calculate the modified values of cluster center. Once you have got the modified values of cluster center, we try to calculate the modified values of the membership values. That will complete the second iteration, and this process will go on and go on through a large number of iterations, and ultimately you'll be getting that particular the clusters. Okay. Now step 4, calculate kth dimension of jth cluster center, that is nothing but CCJK, and the CCJK is nothing but summation I equals to 1 to n mu ij raised to the power g xik divided by summation I equals to 1 to n mu ij raised to the power g. So this is the way actually we update or we calculate the kth dimension of the jth cluster. So kth dimension of the jth cluster is nothing but this. Then step 5, calculate the Euclidean distance between ith data point and jth cluster center. That is nothing but is your Dij. And once you have got this particular thing, now I can update the mu value. That is step 6, update the fuzzy membership matrix mu according to Dij. And this mu ij is nothing but 1 divided by summation m equals to 1 to c Dij divided by dim raised to the power 2 divided by g minus 1 if Dij is greater than 0, and if Dij equals to 1, that is the distance between the two data points is equal to 1, the membership function value is 1.0. Now step 7, repeat from steps 4 to 6 until the changes in mu come out to be less than some pre-specified small value. So the user will have to pre-specify some small value like say 0.001, and to a large number of iterations. So this particular mu value is going to be updated. Then after a few iterations, you will find that there is no significant change in the value of mu. The moment this change in mu value becomes less than equals to that pre-specified small value, we stop. And whatever information we are getting in terms of membership, so we try to form the clusters. Now let us see how to do it. Now here I have designed one numerical example, and it's a very practical numerical example. Supposing that I want to do machining on a free-form surface, something like this. Okay, so this is the free-form surface. Now this free-form surface is actually consists of a number of undulation, ups and downs. Okay, and mathematically it is bit difficult to represent so this type of undulated surface. Now supposing that I want to do the machining for its manufacturing for this particular your the undulated surface or the free-form surface. Now one example, very popular example of free-form surface could be your some sort of cam profile. You might have heard about cam and follower. Okay, so there is a follower profile and there is a cam profile. So cam is going to follow that particular follower. Okay, and that profile can be called as a free-form surface depending on the requirement, or the surface of your mouse used while using the computer. Okay, that could be another example of a free-form surface. Now, supposing that I want to generate this type of free-form surface, very complicated, and supposing that I'm going to use some cutter, CNC machine, and there must be a milling cutter. Now, for the whole region, if I set or if I use the same orientation of the cutter and the same setting of the cutter, there is no guarantee that you'll be getting a very accurate freeform surface. Now, if you want to generate an accurate freeform surface, so what you'll have to do is you'll have to do this particular machining cluster wise. So this freeform surface has to be divided into a large number of clusters. Okay, and depending on this the clusters made, so I'll have to use the machining parameter so that I can do this particular machining very accurately. But before I go for this particular machining, how to do the clustering or how to do the clustering using the principle of Fuzzy-Siemens algorithm, that I'm going to discuss. So I hope you have got the physical meaning of this particular problem or the physical importance of this particular the problem. Okay, now I'm going to represent, I'm going to show you how to solve that particular problem, the problem of clustering. Now, for simplicity, I'm going to consider 10 points 1, 2, 3, 4 up to 10. For each of the points, say I know this x coordinate, y coordinate, and z coordinate. So if I see the freeform surface, on the freeform surface, I'm going to consider the 10 points. And to represent each point, I need three numerical values. That is the x coordinate, y coordinate, and z coordinate. And if I know x, y, and z for all the 10 points, now we can use the concept of Fuzzy-Siemens clustering to do this particular the clustering. Carry out clustering using the Fuzzy-Siemens algorithm. Assume the level of cluster fuzziness G equals to 1.25 and termination criteria epsilon is 0.01. Okay, so what you can do is I'm just going to discuss the solution. The number of data points to be considered, capital N is equals to 10. The dimension of the data, that is L equals to 3. The level of cluster fuzziness, that is G equals to 1.25. And let us assume that the number of clusters to be made, that is C, is equal to 2. So I'm just going to make 2 clusters, okay, out of these 10 data points. But practically, there will be a large number of data points, like a few thousands or few lakhs, okay. But here, for simplicity, for the hand calculation, okay, I'm going to consider only 10 data points. And I'm assuming that I'm going to make 2 clusters based on similarity using the Fuzzy-Siemens algorithm. Now, this particular slide shows the mu matrix generated at random using the random number generator. And what is the size of this particular membership matrix mu? The size is 10 cross 2. Why this is 10 cross 2? Because see, here I have got 10 data points and there are 2 clusters. So for each data point, I have membership function value with cluster 1 and another membership function value with cluster 2. And sum of these 2 membership function values will be equal to 1. You can see that. So this is 0.680551. Okay, this is for the first point, the membership function value in the first cluster, and this is 0.319449. This is the membership function value of the first data point with the second cluster. And if you just add them up, this will become equal to 1.0. So this particular matrix is generated at random using the random number generator. Okay, and so this is the starting membership function matrix, that is mu. And let us see how to update it through a number of iterations. And once you've got the information related to the membership, the way I discuss, I can find out CCJK, that is the kth dimension of the jth cluster center. For example, say I can find out CC11. So here J equals to 1, K equals to 1. That means your first dimension corresponding to first cluster center. That is CC11 is nothing but summation I equals to 1 to n mu I1 raised to the power G xi1 divided by summation I equals to 1 to n mu I1 raised to the power G. And supposing that this is nothing but A divided by B. Now here A is nothing but what? That is your mu I1 raised to the power G. I equals to 1 to n. That means I will vary from 1 to 10. The first data point, second data point, third data point, up to the 10th data point. Okay. And you can see I equals to 1 means what? X11. That is the first dimension of the first data point. If you see the first dimension of the first data point, you can check from this particular matrix. The first dimension of the first data point is 0.2. The second dimension of the first data point is 0.4. And the third dimension of the first data point is 0.6. Similarly, if you concentrate only on the first dimension, the first dimension of the first data point is 0.2. The first dimension of the second data point is 0.4. The first dimension of the third data point is 0.8. And similarly, the first dimension of the 10th data point is 0.8. So I can utilize this particular information here. Okay, xi1. So I can vary I starting from 1 to 10. Accordingly, you insert the numerical values and you insert its corresponding mu I1 and G is equals to your 1.25. And this particular numerical exercise, if you carry out, then you'll be getting A is nothing but 1.912120. Okay, so A will become equal to that. Similarly, you can find out what is B. B is nothing but, once again, that is summation I equals to 1 to n mu I1 raised to the power G. So I can find out the value of this particular, the B. And if you simplify, so you'll be getting B equals to 3.923066. Now C11, that is the first dimension of the first cluster center, is nothing but A divided by B. A divided by B is nothing but this. Similarly, CC12, that is the second dimension of the first cluster center. And if you calculate by following the similar procedure, so you'll be getting CC12 is nothing but this. Now here I'll request all of you to calculate the CC12 and check whether I have calculated correctly or not. Similarly, you can find out CC13 and this will become equal to 0.543316. Then CC21 is 0.554860. CC22 0.459073 and CC23 0.477262. And once you have got all such numerical values, now you can write down the cluster center. Now C1, that is the first cluster center, having three numerical values like C11, C12, C13. C2, that this is nothing but C21, C22 and C23. So you'll be getting C1 and C2 as the cluster center. And once you've got the cluster center, as I told, now you are in a position to modify the membership values like your mu11. If you remember mu ij, that is the membership value of the ith data point with the jth cluster. So this is the membership function value of the first data point with the first cluster, that is mu11, is nothing but 1 divided by 1 plus d11 divided by d12 raised to the power 2 divided by g minus 1. Now I'm using this particular equation, that is nothing but is your, let me show you. So this is the equation. This is the how to update this membership function value. Mu ij, here I equals to 1, j equals to 1. So it is 1, 1. And here you see m equals to 1 to 2 here. Okay. So m will take the value of 1 and 2. Accordingly, you find out and you'll be getting, so your this particular the numerical value. So this is your mu11, and if you calculate, so mu11 will become equal to this, that is 0.888564, as G equals to 1.25. Now to calculate, so this particular mu11, okay, I need the numerical values of D11 and D12. And once you've got D11 and D12, very easily you can write down this particular expression for mu11, and you'll be getting the numerical value like 0.888564 as mu11. Okay. Now similarly, you can find out mu12 is something like this. Then comes your mu21, mu22. So I can find out the modified values for this particular the membership. That completes actually one iteration of the algorithm. Okay, so let me repeat. We start with one set of mu values selected at random. We calculate the cluster center dimensions using the formula. Then after we have got the cluster center values, now we can find out the modified values of mu, that is the membership. And once you've got this particular membership mu value, the modified set of membership values, one iteration of the algorithm is completed. And this process will go on and go on, and through a large number of iterations, okay, which depends on the nature of the data set. So you'll be getting the final cluster center. And supposing that after a few iterations, we get the cluster center like C1 is equal to 0.296189, 0.447977, 0.600323. Okay, this is the dimension which we got for the first cluster center. This is the dimensions we got for the second cluster center. So C1 and C2 you will be getting. And once you've got the cluster center and their coordinates, now you are in a position to get this type of modified membership function values at the end of that particular iteration. Now, supposing that after running this particular algorithm, say we have got so this type of modified values of the membership. Okay, now if you concentrate, what does it mean? The first data point, its membership value with the first cluster center 0.999999, and for the first data point, its membership function value with the second cluster center very low. Similarly, the second data point, its membership function value with the first cluster center is very high, 0.997102, and the second data point, its your membership function value with the second cluster center is very low, 0.002898. Okay, but you see the third data point, its membership function value with the first cluster center is very low, but its membership function value with the second cluster center is very high. What does it mean? It means that data point 1, data point 2, then comes your data point 3, 4, 5, 6, then data point 8, data point 9 are coming into under the umbrella of one cluster. Similarly, the third data point, the fourth data point might be the fifth data point, then comes your seventh data point, and the 10th data point are going to cluster 2. Okay, so this is the way actually we can do the clustering, fuzzy clustering. So the first cluster will contain the first data point, second data point, sixth data point, eighth data point, and ninth data points. Okay, and the second cluster will consist of third, fourth, fifth, seventh, and 10th data points. Okay, so this is the way actually we do the clustering of the data point, and this is nothing but a fuzzy clustering using the FCM algorithm. Now, supposing that we have got the clusters, now we'll have to take one decision whether these particular clusters are acceptable or not. What is the quality of that particular clusters which you have got? Okay, now remember one thing, those clusters will be acceptable if the two clusters are distinct, okay, and at the same time, each of these particular clusters should be compact. So we want the compactness of the clusters. At the same time, we'll have to maintain the distinctness of the clusters. So the clusters are to be distinct as far as possible. Okay. At the same time, the clusters are to be compact because at each of the clusters, I'll be discussing in the next class, there will be a leader that is called the cluster center. And how to select a leader or the cluster center? Now, out of all the data points which are belonging to a particular cluster, that particular data point will be declared as the leader who is acceptable to most of the data points lying in that particular the clusters. Okay, and how to check that I'll be discussing in the next class. Okay, so once you've got this particular cluster, now our responsibility is to check the quality of this particular the cluster. And as I told that I'll be discussing one more algorithm, and the algorithm which I discussed today and the algorithm which I'll be discussing in tomorrow's class, there is significant change in terms of the quality of the clusters that can be achieved. Okay, and how to, and each of these particular methods is having its own merits and demerits. And then I'll be discussing little bit, I'll give you the hints, the way we proposed one new clustering algorithm, which is in between of these two algorithms, so that we can find out the distinct as well as the compact cluster. Those things I'll be discussing in tomorrow's class. Okay. Now in today's class, so we discuss the working principle of fuzzy K-means clustering in details. Okay. And I designed one numerical example and I showed you how to solve that clustering the problem. In the next class, I'll be discussing another algorithm and try to use that particular algorithm on the same data points, and I'll show you how to find out the clusters. But as I told, there will be significant difference between the clusters which you got using the fuzzy K-means algorithm and the clusters which you'll be getting using the second algorithm. Those things I'll be discussing in the next class. Now today, before I stop, like if you have any doubt, so you can ask me, some time is there. And then after I try to clear your doubts, I'll end today's class and the other algorithm I'm going to discuss in the next class. So if you have any doubt regarding today's class, regarding the fuzzy K-means algorithm, you can ask me now.
Sir,
Huh.
sir, like this FCM algorithm seems a lot similar to K-means clustering algorithm.
You are
the
right.
difference being that in K-means, a single element can belong to any one cluster, while over here, element can belong to multiple clusters with different membership value.
You are right.
So this basically captures more information compared to K-means clustering algorithm, right? So yeah.
Actually, what happens in K-means clustering, that is not the fuzzy clustering tool, that is a crisp clustering tool. Okay.
Yes.
Now, fuzzy K-means clustering consider the fuzziness. That means a particular data point may belong to different clusters with different membership function values, which is not done in K-means. In K-means, one data belongs to one clusters only. Okay. Now, this fuzzy K-means is a more practical way of approaching the problem. because a particular data point may belong to different clusters with different membership function values. The way I took the practical example, say a particular student, say student X may belong to different groups, different clusters, and this a particular student X may leave one group and join another group of also. So there is enough fuzziness on the behavior. Okay, so tackling this particular real world problem using fuzzy C-means algorithm is a more practical way of looking at the problem compared to your K-means algorithm. I hope I'm clear.
Yes, sir. That answers the question. Thank you.
Sir,
Huh.
sir, in Lagrange multiplier, what are these lambdas?
Lambdas are actually the coefficient that is called the Lagrange coefficient. Okay, that is called the
Yes.
Lagrange coefficient. If you have like, for example, if you see, I'll show you. If there are n number of your functional constants, the functional constants related to n numerical values sort of thing. Let me come back. You see, summation j equals to 1 to c mu I j is equals to 1.0. So I'll bring this right hand side to the left hand side. So I'll be getting this particular expression. Okay, this particular expression multiplied by lambda I varies from 1 to n. What is n? N is the number of data points. Okay, so this lambda is called the Lagrange coefficient. Okay, now what you'll have to do is, now this is a problem and you can solve it using this type of calculus method, and you'll be getting a set of equations. Those equations are to be solved. And if you can solve and simplify, then you'll be getting this particular expression. So set of equations are to be solved to get this particular equation. Okay. That is the standard Lagrange multiplier method, which is available in any of the textbook. And this is a conventional or traditional optimization tool. Okay, you can see the book by your S.S. Rao or the book by Taha. Might be this is available. Okay.
Okay, thank you.
Sir, one more question, sir. Sir, in this dissimilarity score which you are considering, has there been previous works where they have like did experiments with different dissimilarity scores, like considering Manhattan distance or maybe modifying?
Yeah. There are so many. Not only this Euclidean distance, they consider different measures of distance calculation. Manhattan distance is there. Then there are some other like that is called, just a minute, Hamming distance. Okay,
Yeah, Hamming.
Manhattan distance. There are Mahalanobis distance. There are many other studies.
So is this the best one, or is this
Actually, this Euclidean distance is a widely used method. Okay, but some studies are there on other distance measures also, as you mentioned. There are a lot of work on that direction. Okay.
Hello, sir. Excuse me.
Please.
Sir, my doubt was that if since the data points we are considering, they are with n dimensional, so and we also faced like similar
data points are having L dimension. There are capital N number of data points, each having capital L dimension. Okay.
Yes, sir. So we also faced we did similar kind of thing with in the Vega in optimization. Sir, can we use that, like, and in order to constrain, since it is a constraint of
Vega is an optimization algorithm. Okay, and
yes,
this is a fuzzy C-means algorithm. Inside the fuzzy C-means algorithm, okay, we take the help of optimization algorithm like traditional Lagrange multiplier. Now, if you want to use genetic algorithm or modified genetic algorithm or any other non-traditional tools for optimization, you can do. We have already done it, which I'll be discussing tomorrow in tomorrow's
Okay,
class.
sir. Yes, sir.
Okay.
Yes, sir. Sir, I had another doubt. Like this was just about the means this was actually in the slide 13th actually.
Okay. 30th.
No, sir, 13th.
Oh, I'll have to go back to 13th.
1-3, sir.
Just a minute. Yes. Just a minute.
Sir.
Yes. Tell me.
Sir, here the mu, the c, the lambda, the which are the multipliers, they are the independent variables, right? To if
They
we
are
got the maths of it.
independent. They are independent. This lambda 1,
So-
lambda 2, these are all independent.
So
Okay.
we should write the like partial derivative, right? Like if
No,
we are going to
actually,
not going to get the maths of it.
what we do is, as they are considered as independent, in Lagrange multiplier method, we use the not the partial, we use the full derivative.
Okay, sir. Yes,
we
sir.
use the full derivative. You can see the literature in the Google search. You just give
Yes, sir.
Lagrange multiplier, you'll be getting enough reading material. We use full derivative. Okay.
Okay, sir. Yes, sir. Thank you, sir.
Okay, fine. Any other doubts? Any other doubts? Okay. So if there is no other doubt, let me stop here today. Okay. And you start working for your second test. Start preparing the things. Okay. That will be on 14th October. Okay. Wednesday from 12 noon to 1. Okay. So let me stop here today.